So hopefully by the time you watch this video, you're pretty familiar with the z-test and the z-intervals, things that we do with the standard normal distribution when we're trying to do an inference from a sample mean to a population mean. In this section, we're going to talk about, well, what if you don't know sigma? Okay? And it turns out you have to use what are called t-procedures, t-tests and t-intervals. And we're going to talk about the assumptions here for the z-procedures, the last one being that you know sigma, which is why we have to use t-procedures when we don't. But the assumptions, pretty much for any inferential statistics, your assumption is that you're doing random sampling. When you talk about p-values or confidence levels, those are all based on probabilities from random sampling. If you don't have random samples, then those aren't really valid. Okay? It's also important if you're going to use the z-distribution, the standard normal distribution, that you're talking about normal distributions, normal populations. For the sample mean, the central limit theorem tells us that if the population isn't normal, if we take large enough sample sizes, x bar's sampling distribution will still be approximately normal. So we're pretty safe to use the z-procedures as long as we take large enough sample sizes if we don't have normal population to start with. Another one that sometimes gets overlooked is you're supposed to have independent samples. If the individuals are related to each other, interact with each other, influence each other, then that's putting some bias into it that may give you results that aren't valid under the assumptions of the z-test. Some books will give particular numbers, but let's just say you want your population to be a whole lot larger than your sample. The idea being that if you take a random sample from a large population, the individuals are more likely to be independent there. Let's say they're actual people. If you take a huge population like the entire United States and you take a random sample of 100 people, it's very unlikely that any of those people are going to know each other from that huge population. And then the fourth assumption that I list here, the critical one of why we have this section on the t-procedures, is a pretty unrealistic assumption that in the real world you know sigma. Okay? In the real world, if you need to know sigma, you would have to have all of the information about the population so that you could compute sigma, because that's the population standard deviation. If you had all of that data, you could compute mu. Okay? And if you knew mu, you wouldn't have to do inference from the sample mean to the population mean. So in real life, it's more common to not have sigma and to have to use S, the sample standard deviation. When you do, the procedures are very similar, but the distribution behind it is not the standard normal distribution. It's what we call t-distributions, which are similar but have slightly different shapes, so slightly different computations when we do the area. So yeah, if we don't know sigma, we replace it with S. That's one of the main points if you read through this slide. All of the z-procedures, whether you do the interval or the hypothesis test, in the formula somewhere there's a sigma over square root of n. That comes from the standard deviation of x bar being sigma over square root of n. And there's this term on this slide here, standard error of the mean. Depends on what book you're looking at or who you're talking to. Some will define the standard error of the mean to be the standard deviation from a sample distribution. So the standard error of the mean, SEM, or the standard error of the sample mean, to be more precise, is sigma over square root of n if you define it that way. Some will actually define it to be the approximation that we use for the t-procedures, S over square root of n. So it depends on who you're talking to, what your actual textbook says, so be careful there if you're asked for the standard error of the mean that you're clear in the context. It's either sigma over square root of n or the approximation, S over square root of n. But the most important takeaway here for what we're going to do in the rest of the section, the t-procedures are going to use S over square root of n. Okay, so when we do a t-test, our test statistic, if you remember when we did a z-test, it was x bar minus mu divided by sigma over square root of n. If you replace sigma with S sub x, the standard deviation from the sample for x, then you get the t-statistic. And the t-statistic has a slightly different distribution that we call either the t-distribution, or sometimes you'll see it called the student's t-distribution. And that's because the person who first published the work on this used the pseudonym students, or student. So there's actually not a single t-distribution like there's a single standard normal distribution. You get different t-distributions depending on the sample size or the degrees of freedom, which is a whole nother topic we could talk about, but I'll just say the degrees of freedom for the t-distribution is n minus 1. Okay? If you're talking about n, a sample of size n, they say that n minus 1 of those are free from the formulas, and So the degrees of freedom is n-1 for a t-distribution. So we could match the t-distribution by the sample size, but it's most common if you look in tables or the way we report it, it's usually by degrees of freedom, which is n-1. So each t-distribution, if you look at it, they're slightly different, but they actually approach a standard normal distribution as the sample size gets large. They all have sort of the bell shape. They're single peaked at 0, just like the standard normal, and there's more area in the tails than there would be for the standard normal distribution. But as n gets larger, once you get out to about 30 or so, it becomes very close to the standard normal. Here's some pictures of that. So let's see, the red one in the background here is the standard normal distribution, which is normal with a mean of 0, standard deviation of 1. If you just have 1 degree of freedom, you get the orange distribution here, which has the same sort of bell shape, but it's a little shorter and there's more area out in the tails. If we go to 5 degrees of freedom, then you get this one, the sort of purple color, if you can see the colors there, which is a little taller and getting a little closer to the red one. And then I went ahead and jumped to 30, and you can see by that point it's really close. There's a green graph going along. Again, if you can make out the colors or if you're able to see the colors here, they're very, very close. By the time you get out to 30 for your degrees of freedom or larger, your t-distribution is very close to the standard normal distribution. But in general, there's a little bit more area in the tails. But it's still a density curve, where if you were to find the area between the axis and the graph from two particular, let's say, x values on your axis here, then that would give you the proportion of the population that falls between those values for that variable. So very similar to the standard normal, but a slightly wider shape, I guess you could say. In general, you have more area in the tails. And there's a different one for every degrees of freedom or every sample size, where the degrees of freedom is n-1. And so we have to be careful and define that, or when we do procedures, we have to identify either what the sample size or the degree of freedom is, depending on the software, table, or however we're doing it.